From the Library of Congress in Washington, D.C.
Welcome to our first program of the NASA series in 2018. We are in our 12th season, so we're pretty excited about that. We're just going to keep on going as long as NASA has things to tell us, and they never run out. So we have 7 lectures planned this year, and you can always check our website for the upcoming ones. We'll have one in April, late April. I have no idea what it is. But anyway, I'm Stephanie Marcus from the Science, Technology, and Business Division. And with Sean, who is out of the table, we coordinate this series. Our first speaker, Jonathan Gardner from NASA Goddard, is the perfect person to talk to us about space telescopes. He's been involved with them since his undergraduate days. When he was at Harvard, he spent a couple of summers working on a camera for the Spitzer Space Telescope. And then he went on to do graduate studies at the University of Hawaii, which ain't all that bad. We wish we were there today. And then he had a fellowship in England. So after that, he came back to NASA and did some work on camera for the Hubble, which was placed on the Hubble. And he has been involved with the James Webb Telescope since its early days. And now he is the Deputy Senior Project Scientist for the James Webb. So without further ado, let's welcome him, and we'll go through a lot of history and the future of the space telescopes. Thank you.
Thank you. I'm going to tell you a story. It's one of the biggest stories there is. It started 13.8 billion years ago with the Big Bang. The initial formation of all of the matter, energy, and structure that makes up the universe. The Big Bang started out very hot and very dense, but it was not perfectly uniform. There were some places in the universe that were slightly hotter and slightly denser than others. And those places started to build up over time, get larger and larger through the forces of gravity to form the first stars and galaxies in the early universe. Those galaxies merged together to become the large spiral and elliptical galaxies that we see today, and one of those galaxies is our own Milky Way. Within the galaxies and within our Milky Way, stars continue to form with their planets, their planetary systems, and in some of those planetary systems there are small rocky planets. At least one that we know of has liquid water on the surface. That planet has life and intelligence. So how do we know all this? Well, starting just over 400 years ago, Galileo first took a telescope and pointed it at the sky. And he discovered that the moon has mountains on it. He found that the Venus has phases like our moon. And he found that Jupiter has moons of its own. All of this lent support to the theory of Copernicus that we are not actually at the center of our universe, but are in a typical place. Galileo's telescope gave him a factor of about 60 in ability to observe the sky over the human eye. William Herschel, about 150 years later, used a 49-inch diameter telescope, much more sophisticated than Galileo's handheld telescope. And he discovered the planet Uranus, he discovered moons in the outer solar system, and he mapped what he called the spiral nebulae. His telescope, 49 inches in diameter, gave him a factor of 500 in observing power over Galileo's telescope. Edwin Hubble, the astronomer, not the telescope, was working in the early part of the 20th century, and he had a 100-inch telescope on Mount Wilson in California, and Hubble's telescope had an additional advantage over Herschel and Galileo. The new science of photography allowed him to store up light over time and take longer exposures than simply looking through the eyepiece of the telescope. That also allowed him to show the results that he was getting to other scientists who were not at the telescope. And using this telescope, Hubble further studied the spiral nebulae and was able to measure distances to these nebulae and determined that they were galaxies like our Milky Way but outside of our Milky Way. In this way, Hubble essentially discovered the universe as we know it today. He also was able to measure both the distances and the velocities of these galaxies and found that everything in the universe is moving away from everything else. In this way, he found that the universe is expanding over time, and if you kind of roll the camera backwards in time, you see that that leads you to a beginning to the universe, which we now call the Big Bang. Hubble's telescope and photography gave him an additional factor of 30 over Herschel's telescope. In 1990, we launched the Hubble Space Telescope into space, and over the last 25 years, we have sent astronauts up 5 times to upgrade the cameras and to fix anything that went wrong. By putting the telescope into space above the atmosphere, we were able to get a factor of 10,000, and that factor also includes advanced electronic detectors, just like you have in your phone right now. These advanced detectors give much more sensitivity over the techniques of photography. So, if you ask the question how you win at astronomy, well, this is a logarithmic plot of these factors over time, starting with Galileo's factor of 60 over the human eye, going up to William Herschel's 49-inch telescope. And here we start to bring in photography and then charge-coupled devices, electronic detectors, and then the launch of the Hubble Space Telescope into orbit at the end of the 20th century. So, the Hubble Space Telescope, with its factor of 10,000 over Hubble's telescope, combined with 8 to 10 meter diameter telescopes on the ground and the power of supercomputers to do theoretical modeling, have all led to a revolution in astronomy over the last 25 years or so. So when you talk to astronomers, they use 3 words: we now know. And the reason that astronomers now will say we now know instead of just we know, is because most of us working in the field can remember when we didn't know these things. When I was in graduate school, we didn't have proof of the Big Bang, we didn't know the age of the universe, we didn't know about dark matter and dark energy, we had not detected gravitational waves, although they were predicted. We didn't know of any planets around other stars, even though, again, we were expecting them. The outer solar system had not been mapped, and there was no evidence for water on Mars, or at least not liquid water on Mars. So these are all things that have been discovered since I was in graduate school in the 1980s. And I'm going to take you through a few of these discoveries, sort of a greatest hits of space telescopes of the last 20-25 years. So one of the important discoveries about the universe is that 95% of the mass and energy in the universe is not on the periodic table. And this was discovered 20 years ago in 1998 using supernovae, a kind of exploding star, as a way of getting distances to faraway galaxies. There are several kinds of supernovae, but one in particular happens when a white dwarf star A star about the size of the Earth, a collapsed star, is accreting material from a companion star. So gas from a companion star in a binary system is falling onto the white dwarf, and it keeps accreting more material until it reaches a critical mass. That is the mass at which it can no longer hold itself up against gravity. White dwarf stars are held up by electrons and protons, and if you squish the electrons and protons together enough, they turn into neutrons. A neutron star is the size of the District of Columbia, about 10 miles in diameter. So this star goes from the size of the Earth down to the size of DC and releases a huge amount of energy in as a big explosion, a big flash of light. But the interesting thing about this type of supernova is that it always happens at the same mass. It keeps accreting material until it reaches this critical mass at which, and then it explodes. And because it's always the same size when it explodes, it always ends up to be about the same brightness with the explosion. And by looking at how bright the explosion appears to us, and we know how bright it actually is, that gives us the distance to these supernovae. And they're bright enough, they outshine, for a few days anyway, they outshine every other star in their galaxy. And we can see these to great distances. So 20 years ago, in 1998, astronomers mapping the expansion history of the universe found that the expansion was accelerating and not, as expected, decelerating, slowing down due to gravity. That led astronomers to propose that there was a dark energy that filled the spaces between galaxies that's pushing on the expansion and causing the expansion of the universe to accelerate. Along with dark matter, which is material that is not electrons, protons, and neutrons, but is some sort of exotic material, that means that 95% of the mass and energy in the universe is not actually normal matter that makes up gas, stars, galaxies, planets, people, etc. Gravitational waves, ripples in the space-time that make up the universe, were predicted by Einstein's theory, but although they carry a large amount of energy, they are so tenuous that they're very, very difficult to detect. But just about almost 2 years ago, the LIGO experiment first detected the gravitational waves from a pair of merging black holes. So when two black holes collide, they merge together, and there's so much energy that it puts out gravitational waves. A bit less than a year ago, the LIGO experiment, combined with a similar gravitational wave telescope in Europe, detected the merging of two neutron stars. And these two neutron stars, when they merged together, they put out a lot of light, which was then detected by our space telescopes, by the Hubble Space Telescope, the Fermi Gamma Ray Telescope, and so forth. This was the dawn of what we call multi-messenger astronomy. Previously, astronomers only used light, the electromagnetic spectrum. Light waves are waves in electric and magnetic fields. We now have an additional technique that we can use of gravitational waves in the very structure of space-time. Extrasolar planets were first discovered, normal extrasolar planets were first discovered in 1995, and over the past 20 years we have found several thousand, including with space telescopes. And one of the very powerful techniques that we can use to study these planets is when the planet transits across the face of its host star. And basically that just means when they line up. So the planet goes between the star and our telescope. And so light from the star will go through the atmosphere of the planet be changed a little bit, and our telescopes can detect those changes and measure the constituents of the atmospheres of these extrasolar planets. A very exciting technique that will get to be more exciting in the time to come. So about 2 years ago, there was a discovery of a system of 7 rocky planets, all transiting their host star. And this system is one of the best cases that we have right now for studying the atmospheres of these planets and looking for things like, do any of them actually have liquid water on their surface? Do they have things like oxygen in the atmosphere? Our outer solar system, when I was in graduate school, consisted of Pluto, which we called a planet at that time. Since then, we've discovered what's called the Kuiper Belt, which is a large number of small rocky bodies, rocky or ice planets that we now call dwarf planets, of which Pluto is just one example. That decision to call these dwarf planets was made with the discovery of Eris, which is actually larger than Pluto, and that triggered the political discussion of what we call them. Didn't change what Pluto is, it's just what we call it. And the outer solar system is the repository of the pristine material that formed our solar system. So by studying these bodies out there, these dwarf planets out there, we can determine how the planets in our solar system formed. And the ongoing exploration of Mars has shown that while it's been known for a long time that Mars has frozen water on its surface, we now have evidence that there was liquid water as recently as 50,000 years ago, which isn't that long ago in geological time. So the surface of Mars at times in the past could well have had oceans and lakes. And we have some tenuous, ambiguous evidence that possibly there are things like mudslides currently happening on Mars. So one of the very interesting questions that we would like to study is how did galaxies form in the early universe? The first stars and galaxies form after the Big Bang. And the technique that we've used with Hubble to study early galaxies, the early history of the universe, is to take a picture, and this is the faintest picture that humankind has ever made. We took Hubble and we pointed it at what is essentially a blank part of the sky and just stored up the light over hundreds of hours, a bit more than a month, and then follow-up have brought it, the total investment of time into this image is now approaching a year of Hubble time. These in this image, almost everything you see is a galaxy outside of our own. There are only about a little bit less than half a dozen stars. So everything else you see in the image is a distant galaxy. And some of those galaxies are relatively nearby with light that are the light from those galaxies have been traveling through over time to get to us. And so as we look at galaxies that are further and further away, we're seeing light that was emitted longer and longer time ago. And some of them, the fairly bigger ones, are about 1 billion light years away. But some of the galaxies in this picture, the very faintest ones, can be as much as will have emitted their light at less than 1 billion years after the Big Bang. So we're looking back almost 13 billion years in time over the history of the universe when we look at these very faint, distant galaxies. And this is the biggest investment of time with the Hubble Space Telescope was in this experiment, looking for the very early history of the universe. And one of the interesting things that we found was that when we study these very distant galaxies in detail, some of them are actually several 100 million years old. So this is several 100 million years old at just 1 billion years after the Big Bang. And this is the faintest that Hubble can go. So if we want to go further back in time, we need to find galaxies that are even more distant and catch them at the point where they are first starting to form their stars. This has led us to decide that we need that we need a telescope that is bigger than Hubble, that can collect more light and see more fainter galaxies, more distant galaxies. But there's another aspect to these very distant galaxies, and that is as the light is traveling from the galaxy to us through the expanding universe, the light is stretched out by the expansion of the universe over time, so that light that is emitted as visible light or ultraviolet light has been stretched out so that it appears to us in the infrared. Infrared light was discovered by William Herschel as well when he took sunlight, broke it up with a prism, and showed that a thermometer here beyond the red would start to heat up. Infrared light is light just like visible light, but with longer wavelengths. But it's also what happens when you've got when something is at a temperature. It's got a temperature associated with it. Now, most of the sun's energy that reaches the surface of the Earth is visible light. That's not a coincidence. We evolved to be able to see the light from our primary star. But infrared is heat. And here are a few infrared pictures. First of all, there's a picture of a man holding a lit match. So the brightest part of this infrared picture is the flame of the match. The coolest part is the tie, which is away from his body heat, and his glasses, which again are cooler than his face. This is an infrared picture of a cat, and again the coolest part of the picture is the cat's fur. It's a good insulator, but the eyes and the mouth are close to the inside of the cat's body, so they're the warmest parts, the brightest in the infrared. You might be wondering what the third picture is down here. Well, this is actually a visible light picture of a floor where somebody used to be standing, but they've walked away. But when we look in infrared light, we see that the person's feet has heated up the floor, left the infrared picture behind. So, in order to see these very distant galaxies, the first galaxies to form in the early universe, we not only need a telescope that is bigger than Hubble, but we also need a telescope that can work in the infrared. So going back to how we win at astronomy, well, the answer is big telescopes with sensitive detectors in space, and that has led us to build the James Webb Space Telescope, providing an additional factor of 100 over the capabilities of the Hubble Space Telescope. Webb is the successor to Hubble. Successor is not the replacement. We'd love to have them both working together, and it looks like we can do that. But the James Webb Space Telescope will be a large, cold telescope in space, and I'll be telling you about that in the rest of this talk. So the first The first science idea we had for this, for what should be the successor to Hubble, was to find the first galaxies that formed in the early universe. That's what we call the study of origins, because beginnings are very important when you have the way something starts out can tell you the initial conditions for changes over time. But in things that are complex, like babies and galaxies, studying those actual changes over time are also very important, and that's what we call evolution. So the science of Webb is the beginnings, or the origins and evolution of galaxies. So pictures like the Hubble Ultra Deep Field we will do with the James Webb Space Telescope, going fainter and into the infrared to find the first galaxies that formed in the early universe. We will then trace those galaxies over time to see the formation of the spiral and elliptical galaxies that we see today, spiral galaxies like our own Milky Way. It turns out that a large infrared telescope is also very good at studying the formation of stars within our own galaxy. So that's what we have here. Stars form in clouds of gas and dust. And when stars form, they also form planets. And the study of planets, both around other stars and planets in our own solar system, can tell us about the conditions that might make it possible for life to develop on those planets. So going through these one by one, looking at supercomputer simulations, this is a simulation of the formation of the first galaxies. The universe started very dense and very hot, but in some places it was slightly more dense, and in those over-dense places, material started to fall in, both dark matter and then eventually the ordinary gas of the hydrogen and helium that was formed in the Big Bang started to fall in. Eventually, those clouds of gas formed the first stars, and that's what we call the first galaxies. They started out actually fairly small and then built up over time as galaxies merged together. Many galaxies today live in groups. This group of 4 galaxies, and you can see the difference between the spirals galaxies and the elliptical galaxy down here. In these groups of galaxies, or in bigger clusters of galaxies, galaxies do collide with each other. And when 2 large galaxies collide, they don't collide in the way that cars collide. They don't go bang. They kind of go slosh, because most of the space in a galaxy is empty space. The stars that make up the galaxy are very small in comparison to the distances between the stars. And so 2 colliding spiral galaxies, as you see in this supercomputer simulation, will slosh together, interacting through gravity. The gas will interact a little bit through pressure, but mostly it's all gravity. And as the spiral galaxies collide, they get mixed up, they lose their spiral structure, and the end result is something that looks a lot like an elliptical galaxy. Again, within galaxies, the stars will form, and particularly after the first generation of stars, the primordial gas of mostly hydrogen and helium has been processed through stars and through supernovae exploding stars, returned to the gases between the stars, and the heavier elements have been formed, and those elements become dust. When a star forms in the center of a rotating cloud, the material in the outside of the clouds will gather together and through gravity and form the planets. The small rocky planets we think are formed closer to the stars, and the gas giants are formed further out, along with the ices. After the planets first form, sometimes there are planets that are in very similar orbits near to each other, and we see evidence for giant collisions in some stellar systems. This is also the leading theory for the formation of our own moon. The early Earth, shortly after it formed, was impacted by another planet about the size of Mars that kicked up a huge cloud of dust that filled the whole solar system. And we see other solar systems that have these giant dust clouds. The material was knocked away from the Earth and reformed to be the moon, and the Earth formed again from what was left over. So all of these are, so that's another one of these we now know. And some of the evidence for that actually came from the Apollo moon landings and the rocks they brought back. Okay, so in comparison, a comparison between the Hubble Space Telescope and the James Webb Space Telescope, its successor, Hubble is a telescope that's kept at room temperature. We have sent astronauts up there 5 times, and so we maintain the telescope at room temperature so that the astronauts can interact with it. The James Webb Space Telescope is designed to detect infrared light, and the problem with a telescope designed to detect infrared light is that the telescope itself will be glowing if it's at room temperature, and that applies both to the Hubble Space Telescope and also to all the telescopes on the ground. They are all glowing in infrared light. So in order to make the James Webb Space Telescope cold enough to detect infrared light, we are going to cool it down to 225 degrees below 0 Celsius. That's minus 370 Fahrenheit, or about 50 degrees above absolute zero temperature. And we do this by putting the telescope behind a tennis court-sized 5-layer sun shield. This is one of the layers of the sun shield being built up. Hubble is in what we call low Earth orbit. It's 375 miles above the surface of the Earth. It goes around the Earth once every 90 minutes. And but the James Webb Space Telescope is going 1,000,000 miles away. It will be launched on an Ariane 5 rocket. This is a European launch vehicle and is provided as part of the European contribution to the James Webb Telescope mission. Webb is a joint project of NASA, the European Space Agency, and the Canadian Space Agency. So Europe is providing the launch, and it will be going 1,000,000 miles away to a special orbit called the second Lagrange point. The second Lagrange point, as the Earth goes around the Sun once per year, the second Lagrange point goes around the Earth once per year, keeping the Sun and the Earth and the telescope all in a line so that we can have both the Sun and the Earth on the warm side of the sun shield, while the telescope is on the cold side, cooling down to 225 degrees below zero. As I said, we want to have a telescope that's bigger than Hubble so it can collect more light, see more distant galaxies, and look further backwards in time. So Hubble's primary mirror is 2.4 meters. That's just about like that big. Webb is 6.5 meters, which is about the size of this room. Now, as I said, Webb will be launched on an Ariane 5 rocket, and the diameter of the Ariane 5 is 5 meters, which brings up the question, how do you fit a 6.5-meter mirror into a 5-meter rocket? Well, the answer is that you fold it up. So here's a picture, animation of what Webb will look like after it launches. It's launched all folded up, and we will unfold it in about the first 2 weeks after launch. So the first thing that comes out is the solar panels to provide power and the communication antenna. And then we'll start to unfold this tennis court-sized 5-layer plastic sun shield. The sun shield is launched within these covers. We fold those back, and we start to pull out the sun shield. The sun shield is made of a plastic material called Kapton, and each side of it is actually different, but the side facing the sun is very highly reflective to reflect the sunlight away. The 5 layers are each about a foot, a little bit more than a foot apart, and of course this is in vacuum, so this works like a giant vacuum flask where the heat can escape between the layers of the sun shield. Each layer is colder as you get to the telescope. The last 2 deployments are the secondary mirror on its support structure, and then the 2 side wings of the primary mirror are folded out. The mirror itself, the primary mirror, is made up of 18 mirror segments. They're each made of beryllium, which is a very lightweight, stiff metal. And they're coated in gold, which is highly reflective of infrared light. You can see each of these mirror segments is a hexagon so that we can tile them together, and it's 1.3 meters across each segment. We installed the 18 mirror segments onto this backplane support structure, and I'll show you how we did that. This was done at the Goddard Space Flight Center a little bit less than 2 years ago. We used a robotic arm to place each of the mirror segments onto the backplane, and then the technicians attached it. While we were doing this for protection, we had these black protective covers on the mirror segments. And this process has been completed, and then when it was all done, we took the protective covers off, revealing the gold mirror surfaces. Here's a picture of the telescope itself, again in the Goddard clean room. We have a viewing window, and that made a good opportunity for selfies. Here is the senior project scientist for Webb, Dr. John Mather, a Nobel laureate. He won the Nobel Prize essentially for proving the Big Bang. I'm his deputy on this project. I wasn't actually there when they did this, when they scanned the mirror across, but I was able to have a picture of myself taken with the mirror. And this is probably the coolest selfie I will ever take of myself reflected in a multi-billion-dollar gold-coated space telescope mirror. This is a very cool picture as well. This is done within the clean room, the technicians who worked on the mirror, and reflected in the mirror is the NASA logo from the back wall. And one of the interesting things you can see is that this is not a flat mirror like you have in your bathroom. It is actually a lens to focus the light, and so they were able to line up the NASA logo to fill the whole mirror. On back of the telescope, we have 4 cameras. They each has a different capability, including taking pictures in visible light and infrared light. Webb is capable of detecting the redder colors of visible light. It stops at gold color because the gold itself absorbs everything bluer than that. And it works out to out into the mid-infrared. These cameras were installed together into a structure seen right here, and this shows the installation of the camera package into the back of the mirror, which is upside down. So the mirror is pointed down in that structure. Again, this was done in the clean room at the Goddard Space Flight Center up in Greenbelt. And you can see, again, the viewing window had lots of people in it. I actually arrived to watch this just right at the very end. You can't see me in the video because the camera moves right at about the time that I arrived. You can see that there's a lot of people involved. There's both the people who are doing the work and the people who are watching to make sure everything is done, the quality assurance and safety people. So right at about this point is when I arrived, and I was able to watch it go in. Okay, and the sun shield is fully assembled and installed onto the spacecraft. We now have the Webb telescope or the observatory is now in two pieces. We have the spacecraft and the sun shield fully done and currently undergoing testing. We have the telescope and the instrument package were tested at the Johnson Space Flight Center last fall. They were there during the hurricane. Both the equipment and the people were okay. It was kind of an exciting time for them, though. So this is the vacuum chamber where we tested the telescope and instruments. It was actually built for the Apollo program and is human rated. So the astronauts practiced walking on the moon in their spacesuits inside this chamber back in the 60s. The Webb project took out the simulated lunar surface and put in a inner, what's called a shroud that was cooled with liquid helium to get down to the cold temperatures to test Webb. And here's a picture of the telescope after that test, which lasted 3 months, when it was complete. Moving this large telescope around, we have a special shipping container. We actually, to go from Goddard to the Johnson Space Center, we actually took the telescope on the Beltway. It goes at a maximum speed of about 7 miles per hour, which made it very popular with the people who were on the Beltway at that time. But we do this in the middle of the night. So it went from Goddard to Andrews Air Force Base, then flew on this C-5 cargo plane. We put the whole truck, including the cab, inside the plane and flew it down to Houston. This is this shows how we drive it around, going very slowly to make sure that it doesn't bump too much. And you can see, again, 4 a.m. Then taking it on the roads is an interesting thing because it's so big. You can see that we have a crane here that pulled up the street lights to get them out of the way as we drove it around. So the telescope now has been, was completed the test in Houston and was flown to the Northrop Grumman facility in Los Angeles, where we're building the spacecraft and sun shield. Oops. And so now we have all of the parts of the observatory in the same clean room. Here it is arriving in Los Angeles. Again, the telescope with the side wings folded up. The instrument package is in the inside, and you can see the rest of the primary mirror here on the bottom. And then this is the sun shield in its launch configuration. So it's all folded up with protective coating around it. The spacecraft, which maintains position in its orbit, is down here. And this structure is a simulation or a mass model of this. And we're still going to be doing some more testing of the spacecraft and sun shield. And then towards the end of this calendar year, we'll put the two together, do some final testing, and then we're ready for launch. Launch, as I said, is from South America, Kourou, French Guiana. And after this is all put together, it becomes too big to fly in that C5, so we're going to go by boat through the Panama Canal. So, if you would like to learn more about the James Webb Space Telescope, we have a website, of course, jwst.nasa.gov, a constant stream of news. You can see down here the latest news is this talk. But we also, whenever we make any progress, we put it out on the website. We have Facebook accounts, Twitter feeds, and other social media. So stop in and keep tabs on how we're doing. Here's a picture of a couple of our fans. You can see on the set of The Big Bang Theory, we've got a model of JWST back here and some of our pictures. Webb was designed to study some age-old questions that date back to the beginning of humanity. Where did it all come from? What are the origins? What are the changes over time? What is the process that went from the Big Bang 13.8 billion years ago to the formation of galaxies, stars, planets, and life and intelligence? Where did it all come from? So I'd like to thank you for your attention. I'm going to leave you with one quote from somebody who inspired me when I was the age of my children in high school, Carl Sagan. He said, "Somewhere something incredible is waiting to be known." So thank you for your attention. I'd be happy to take questions.
Thank you so much. We now know a little bit more, and it's kind of fun to go behind the scenes to see this all put together. So please ask your questions, and he will repeat them so everyone can hear.
So
Okay.
why is it being launched in South America?
Question is, why is it being launched in South America? So the decision to use a European launch was part of the early negotiations for in putting together the partnership. It's not that the U.S. doesn't have launch vehicles, but that was what was worked out that they would contribute. So where do you want to put your launch site? It's good to be on a coast so that you can launch it over the ocean. It's good to be on the east coast so that as you launch it over the ocean, you get an additional boost from the spinning of the Earth. You launch it over the ocean just in case something goes wrong. If pieces fall down, they go in the ocean. But you want to launch east, heading east. So launches on the east coast. And additionally, particularly if you're going into deep space, you want to launch as close to the equator as you can. So the U.S. primary launch site is in Florida. Again, it's south, so it's close to the equator. It's on the east coast, and the launches go out over the Atlantic Ocean. The European launch site is in French Guiana. French Guiana is a part of France. It is as much a part of France as Hawaii is a part of the United States. So they have the infrastructure of being part of France in a place that is on the east coast of the continent and near the equator. Question?
How many extra panel segments did you have to make as backup?
How many extra panel segments did we make as a backup? So there are 18 in the telescope, and because a hexagon has six-fold symmetry, that means there are 3 different kinds of those in those 18 segments. essentially, we call it prescriptions, so 3 different optical prescriptions. And those are then repeated 6 times to make up the primary mirror. So we have 3 spares, 1 of each optical prescription.
What's the anticipated life of the Webb telescope?
What is the life of the Webb telescope? So the lifetime is limited by one thing that we use up, and that is fuel. We need to use fuel to maintain its position. It's actually in orbit around the L2 point, not right at the L2 point. So to maintain that position in orbit, we need to fire the rockets about every 2 weeks or so. In addition, the sun shield acts as a solar sail, and the telescope can build up angular momentum, which we store in reaction wheels, and we also need to use the fuel to get rid of that angular momentum. A telescope like Hubble is in low Earth orbit. It uses the Earth's magnetic field to get rid of angular momentum, but with Webb we don't have that, so we need fuel. So we need to have fuel. Fuel is the ultimate limiter of the lifetime, and we have 10 years of fuel on board. There's some margin in that, so we have a bit extra, and we actually use a lot of our fuel, of our onboard fuel, to do the final orbit insertion after launch. So if launch goes well, we have extra fuel that we can use for lifetime. But there's a 10-year requirement for lifetime. We also, the other thing that limits lifetime, can limit lifetime, is if something goes wrong. And we mitigate that by doing lifetime testing. So we will take an exact copy of our mechanisms and run them through however many times we expect to use during the mission. And we're actually doing lifetime testing for 5 years because that's a very expensive thing to do, to ensure that parts will last and keep working for 10 years. We tend to only do that if we're sending something out to Saturn, where it's going to take 10 years to get there. So lifetime testing is 5 years, but that's always done at a factor of 2 anyway. So we expect 10 years.
If it were to live beyond its plan, is there a plan for replenishing fuel if you found that it's doing real well after 10 years?
So the question is, if it's doing well after 10 years and we're running out of fuel, can we refuel it? There's always a plan. What there isn't is funding. So there are people that are looking at this. In general, the servicing of satellites, including refueling. Webb is not designed to be serviced or refueled in the way that Hubble was designed to be serviced, and we don't have the capability to do that. But 10 years is a long time. Yeah.
What is the fuel that's being used? Is it liquid? Is it nuclear?
So the question is, what is the fuel? It's something called hydrazine, and I'm not a propulsion engineer, so I'm not really sure what that is. But it's certainly not nuclear. No, it's not a very powerful rocket. The fuel that we have is, I think, 300 kilograms, and that will last 10 years. So it's mostly just doing small nudges. Especially once it's all deployed, we don't want to do very much acceleration, so it's very gentle. It's not a solid fuel, no. No, it's either liquid or gas, and I don't know which one. Probably liquid. Yeah. Yes.
Is the Hubble the biggest and the best in the world, the telescope?
Is Hubble the biggest and best telescope in the world? Well, first of all, it's not in the world. It's above the world. It's in space. So Hubble it's not the biggest telescope we have. The biggest telescope we have is a ground-based telescope called the Keck telescope that's 10 meters in diameter and therefore even bigger than Webb. But by being above the atmosphere, that makes Hubble much more powerful than telescopes that are on the ground. There's always a bit of a trade-off. To build a telescope that's in space, going to go to space, you have to make sure that it can work remotely, in most cases without ever having the chance to fix it. And even with Hubble, it was very, very expensive to go and fix it. Whereas telescopes on the ground, you put it together and you start it working, and if something's wrong, you just fix it. And if you have new technology for your cameras, you can just build a new camera and put it on and so forth. So essentially what we do is that we don't ever do anything in space that can be done from the ground. If we can do something with a ground-based telescope, then that's going to be cheaper than doing the same thing in space. So space telescopes are designed, all of them, designed to do things that we cannot do from the ground at all. So yes, in a sense, Hubble is by a lot of ways of measuring it, Hubble is the most productive telescope in history. It's the most powerful telescope in history, and has contributed to the most discoveries. But that's partly because it's unique. And likewise, Webb will also be unique. It will do things that we just cannot do from the ground. There are also even bigger telescopes being built on the ground, going up to 25 to 30 meter diameter telescopes. Those will also be incredibly powerful, particularly working together with each of them using their unique capabilities.
What are the plans for Space Telescope or other telescopes after the Webb telescope, beyond the Webb telescope?
So what are the plans for space telescopes after Webb? Well, so getting a little bit into scientific politics for a minute, the National Academy of Sciences holds what they call a decadal survey every 10 years to recommend to NASA. They make recommendations to NASA, to the National Science Foundation, for what to do in astronomy and astrophysics over the next decade. And Webb was the #1 recommendation for NASA in astronomy in the year 2000, and that started the project building Webb that's now culminating. In 2010, there was another decadal survey, and the Academy panel recommended a project called the Wide Field Infrared Space Telescope, or WFIRST. This is a telescope that is the size of Hubble, but has a much, much larger field of view, a factor of 100 times bigger part of the sky, and it will do big surveys across the sky, aiming at, in particular at 3 scientific questions. One is, what is the dark energy? How can we characterize the effects of the dark energy on the history of the universe? So in comparison to the original discovery of dark energy was made with study of about 40 supernova, these particular type of supernova. Further study with WFIRST will have hundreds to thousands of those type of supernova, get a much better measurement, and learn more about the properties of the dark energy. That telescope also will be looking at exoplanets, both through a statistical study, looking at all of the exoplanets in a region, looking towards the center of our galaxy, and then also using a technique called coronography, where it puts a spot in front of the star and tries to detect the light from the from the planet itself. And then finally, because it's a big survey telescope, it's going to discover lots of new types of things that can be used for lots of other astronomy questions. So that was a recommendation from the 2010 decadal survey. And we're in the design phase of that telescope. And then what comes after that will be up to what we call the 2020 decadal survey, which is just being formed. They're just, the National Academy is just starting to choose the members of that committee. These decadal surveys are a big process. They ask for submissions of white papers from astronomers across the country. They usually get about 200 suggestions of what to build. In the running for the next big space telescope include telescope that would be even bigger than Webb and would be optimized to study extrasolar planets, in particular looking at rocky planets and trying to find what we call biomarkers. So things like, for example, in the Earth's atmosphere, ozone and methane are in disequilibrium because of the presence of life on Earth. We're affecting life in general, going from bacteria to people, affects the atmosphere of the Earth in a way that if there were no life would not be sustainable. So looking for that kinds of things is one of the big questions that we need an even bigger telescope than Webb and something that's optimized to do that. So that's one possibility. Other possibilities in the running include a big X-ray telescope to study black holes and a gravitational wave observatory. Anyway, there's a number of different possibilities for what comes after W first. So we have Webb, then W first, and then the next big thing. Yeah.
Hubble was afflicted with some initial aberrations that were fixed by Story Musgrave, I think, in the spacewalk.
Mm-hmm.
Can you characterize those, that force, and what you do to make sure that there's nothing wrong with it?
Right. So the question is, Hubble was launched with some aberrations on its mirror that were fixed by the astronauts, and what are we doing with Webb? So first of all, the problem with Hubble was that the mirror was ground was shaped precisely to the wrong prescription. There was a problem with the test equipment that was making a highly precise mirror is somewhat of an iterative process. You polish it into a shape, you measure the shape, you polish again, and go back and forth. And with Hubble, there was a problem with the test equipment, and so they ground it perfectly to the wrong shape, which meant that when the astronauts could go up there, they could install a corrector lens that exactly fixed the problem, because it wasn't an error or a roughness problem. It was just the wrong shape. So one of the things that was done with Hubble to save money during its construction was that they did not do a full end-to-end optical test where they shine light on the primary mirror all the way through to the instruments to measure that light. That's a very expensive test. With Webb, since we don't have a plan for servicing, we did that test. That's what we did in Houston. Took 3 months, just a 100-day long test. We did shine light onto the primary mirror, bounced into the secondary, into the instruments, and measured that that everything was okay. During that test, the vacuum chamber took 7 tanker trucks of liquid nitrogen per day. That just kind of shows the scale of that test. There were about 50 people working 50 people on each shift, and it went round the clock. During the hurricane, we almost ran out of liquid nitrogen, and so the president of the company was called, and he ordered that extra trucks would come in during the hurricane. So this was kind of an all-hands-on-deck type of thing, and that testing is what will ensure that that Webb will work. Now, the specific problem with the mirror that Hubble had, Hubble has a solid glass mirror, whereas Webb has the 18 mirror segments. Each mirror segment is adjustable on orbit, and we plan to adjust them about every 2 to 3 weeks during the lifetime of the mission. We'll tweak up the positions of those 18 mirror segments. Each one of them can be moved 6 different ways, so that's back and forth, up and down, tipping, tilting, and rotation. That's 6 different degrees of freedom. We also have a thing that can poke the back and change the radius of curvature of each of the mirror segments. All of that together means that we could take out a lot of the exact type of problems that that the Hubble mirror had. But basically, Hubble is actually an exception. It was the only major NASA Space Telescope or mission that was designed to be serviced in the way by the astronauts. And it was designed from the very beginning with servicing as part of the plan. Webb, because it's going 1 million miles away, because it's a big, very floppy structure, and because it's cryogenic, it's at those ultra cold temperatures. All of that led to the decision that we would not plan to do the servicing. That's something that kind of goes back and forth. The question of, do we plan for servicing? And some of the future missions, they're looking at servicing again as a possibility.
It seems like a huge risk that it's not serviceable. So if there's, and it's obviously very complex, so it seems like there's the slightest problem here. You put all your eggs in one basket.
Yeah, so the question is, that seems like a big risk. If there's a problem, then we don't have a way of fixing it. So in addition to a complex testing program where we test everything at multiple levels. So we will get a detector and we test it. We put it into the camera, we test the camera. We put the camera into the structure, we test that. We put that together with the telescope, we test that. There's this hierarchical way in which we are testing everything multiple times as we put it together. So in addition to that, we also have backups for every credible single point failure. So for example, electronics, we have dual electronics and we can switch back and forth between them. So if an electrical component goes bad, we can bypass that and bring the signal around on the other side. All the motors, all the mechanisms have dual windings, so we can we have a backup for that as well. The deployments themselves can be done in both directions, so we do it. If it doesn't latch, we can go back and try again, and so forth. Essentially, yes, you're right. It's risky business, but this is what NASA normally does. Hubble is the only big project that was designed to be fixed in orbit. Yeah.
How soon after launch will it be positioned, and will it start to actually provide data?
So the question is, how soon after launch will it be in position and doing science? So it will finally be ready 6 months after launch. That 6 months, it takes about a month to get into position and to do all of the deployments. It then, once the sun shield is out, it starts to cool. When it's cold enough that we can turn on the cameras, which don't work at room temperature, we will point the telescope at a bright star, and we'll see 18 different out-of-focus images of that star. So then we have to move the 18 mirror segments so that they all line up to a perfect uniform optical surface. That's a process we call commissioning the telescope. That will take another 3 months or so. And then we have 2 months for turning on all of the cameras and checking out all of the different filters and modes and so forth. So the plan is to start routine science observations 6 months after launch.
I guess we'd better end. Thank you so much.
Thank you for coming.
This has been a presentation of the Library of Congress. Visit us at loc.gov.